Hello everybody, welcome back. In this lesson, we will go over examples for the quotient rule. And this practice will be pretty similar to what we did in the product rule. Therefore, without a further ado, let's start working with examples right away. First of all, let's recall the formula. The formula is none other than just like here, you have a quotient, a function divided by another. Right away, you can see there's a precedence, right? There's an order for this function. This is the top and this is the bottom. So now in this setting, first of all, you're going to grab the top function and take the derivative f prime and multiply it with the original second function and then minus original first and the derivative of the second. And then the whole thing is divided just by the algebraic square of the bottom function. So this is just grabbing this function and squaring it and put it right there. So there is no calculus involved in it. But the recipe for the quotient rule is right here. So follow it carefully. Let's play with an example. So the first step, now here you have top function and the bottom function. You can identify them without any ambiguity. So let's try to take the derivative of the top. When you take the derivative of the top, it is none other than just the derivative of x squared, which is 2x, and then the derivative of plus 1 is going to be just 0. Therefore, 2x tan x. And then don't forget the minus sign. Here we have a minus sign inside that formulation, so minus. Then you have original top function multiplied with the derivative of the bottom, which is secant squared x. Now, once you do that, all you need to do in the next step is to grab this bottom function and square it and put it underneath. So you can write it like tan x square, or more precisely, or like let's say more commonly, you can just write it like tan square x. When it comes to trigonometric functions, when you square them, you just call it as a square of that operation itself. For convenience, it is just a notation. And then this is our answer. We're not going to simplify it any further. Let's play with one more examples. Now here, before proceeding, why don't you take a moment and see if you can get the answer yourself. Take a moment and try to simplify. And the goal is to get the answer, write down the answer in one single line, in one single step. Take a moment. All right, I hope you gave it a try. Now, the derivative of the top, that is none other than just cosine x multiplied by the original bottom function, which happens to be 3ex minus original top is none other than sine x, and then you're going to take the derivative of the bottom function. So this derivative has the constant multiple rule, where you have just 3 times and then the derivative of ex, so which happens to be 3ex itself, as it is. The whole thing is divided by the square of the denominator, the square of the entire function. So make sure that you put the square together, and that's our answer. Potential simplifications that you can have here, even if you do not simplify, this is perfectly fine. Potential simplifications and variations of the answer. So one thing that you can do is to simplify squares separately. You have 9 e to the 2x when you simplify it. On the other hand, you can factorize 3 here, and that could potentially simplify with one of the 3 factors. Here in the denominator, there are 2 factors due to this squaring. You can simplify it. That simplification can be even performed like this, right here, right at the beginning of the problem. This 3 in the denominator is an algebraic multiplication. In other words, you can bring it out as the product of 1/3 just to get rid of this 3 here. You can do that. If you do that, you essentially have constant multiples of 1/3 in front, and you differentiate sine x over ex. So it's up to you which way you're going to proceed with. But if you have that constant multiple approach, make sure right after that factor 1/3 you have parentheses or brackets to enclose everything, because 1/3 is a factor that belongs to everything. All right, let's proceed to one more example. Now have a quick pause and try to work it yourself. Yes, we can do this right away, right? Now we can take the derivative. First of all, the derivative of the top, secant squared x times the derivative times the original second function sine x minus original top minus okay, so the derivative of the second function, that's going to be cosine x. The whole thing is divided by the square of the sine x, and that is our answer. Now there are potential simplifications that you can have in this scenario, right? For instance, tan x times cosine x, that's none other than just sine x. And there you already have a copy of sine x here, so there's a potential simplification of this entire solution. However, I'm going to leave the answer like this because that's the correct answer, even if you do not simplify. However, if you're curious about the simplification, this is pretty similar to, pretty analogous to one of the problems that we solved earlier with the product rule. Look at this. Method 2. Infusing a little bit of trigonometry from trig knowledge base. So tangent x is none other than sine x over cosine x, and then sine x in the denominator is just 1 over sine x. Can you see this simplifies right away, leaving the derivative of 1 over cosine. But look at this, 1 over cosine is none other than just secant x, where you have a direct derivative listed on your toolbox. If you take the derivative, you're going to get secant x times tangent x. Now, if you do not believe this answer, this is my recommendation, this is my invitation. Simplify this answer right here. Simplify it until you see this simplified answer in your response. That is for additional practice. For your calculus computation, you can just stop right here. But learning is not just about getting an answer and just throwing it in the trash after that, because celebrating an answer is not the only thing that we need to have, right? We need to learn even from an answer what we got, right? After earning an answer, after having an answer, look at it, think about it. So that's what you can do as a when you learn further, when you explore uh, a subject. It should not be just getting an answer, it should be something more, right? So let's proceed to another example where you have yet another simple problem, right? A direct quotient rule. The derivative of the top, 5x to the fourth times ln of x minus, and then this times x to the 5 times the derivative of ln of x, which is the bottom function, that's going to be 1 over x. The whole thing is sitting at the top of the square of ln of x. So potential simplifications, here you can simplify these two. It might be a good idea to simplify those two terms because that is an evident simplification. So you have 5x to the fourth and ln of x minus x to the 4 divided by x is none other than x to the 5 divided by x is x to the fourth. The entire term is divided by just, and that would be sufficient as a simplification. One more example. Here we do have an example where we have more than only two functions. Can you see? Here at the top, we have two pieces combined. Now, this is exactly what I mentioned earlier. Once we learn these methods, when we learn different techniques of differentiation, then at the end, the best results or the best computations will arrive when you infuse them together, when you just put them together and see how beautifully they go along with each other. Now, in this scenario, I'm going to take the derivative of the top. If you feel it is too much to do right at the beginning, just indicate it and save it for the next step. I'm going to take the derivative of the top function, but don't forget it is a product already. So I will leave it for the next step and take the derivative of the second one, the bottom function, which is negative sine x. And then minus the original top function. Oh, sorry, I made a mistake there. I should correct it. The derivative of the first function together with the original bottom function. It should be just cosine x, right? So even I made a mistake when I worked with this example. So do you see how much of attention that you need to have when you compute these components? Always think about it. When you take the derivative of one component, the other one stays as it is. And then the original top function, xex, and then the derivative of the bottom, which happens to be just negative sine x. And then the whole thing is divided by just square of the bottom, which happens to be just cosine squared x, or in other words, the complete square of cosine x. Now, our answer is not complete until we do this. Now, if you really hate to get to two lines for these answers, you can see like most of these answers can be done in one single line. If you'd like to have that practice, do this computation right away in the very first step, but make sure that you have parentheses. And at the same time, when you overwhelm your answer with more computations in one single step, make sure that you have enough practice not to miss any key components. So at this point, I'm showing you this step-by-step approach so that you can do it in the next step. But essentially, you can jump right to this step that I'm about to write when you earn more practice, when you have enough practice. So when you take the derivative of uh, the first component here, let's have it, just have parentheses here, and then the derivative of the first one, it's 1. ex plus, and then original first and the derivative of the second, that's going to be just ex times, now we're done with the derivative, this component, and then we have cosine x just as a product right here, and then minus xex. In fact, you can combine these two negative signs to make it plus right in front. I will update it, plus sine x. The whole thing is sitting at the top of cosine squared x, and that's our final answer. Potential simplifications or different ways of writing. Now, 1 times ex is none other than just uh, ex itself. And if you'd like to take a common factor ex out of the first two terms, you can do that. If you take ex component out, you can have another factorization step in the next uh, step. That would be just, again, taking ex all the way out of this simplification. You can do that, but even if you leave the answer like this, it's perfectly valid and perfectly fine. So let's say, consider this as a capstone problem. Seems complicated now. In this scenario, right, it is not complicated. In fact, what we're trying to do is to do this answer in one single line. All you need to have is clear attention on each step. Let's follow the quotient rule, the top and the bottom. Now here I'm not going to spend two lines for this problem. I will fix my answer. I will fit my answer to one single line somehow. Let's give it a good try. The space could matter, but the method is going to be just that simple. I mean, it's going to be simple and you can write it right away. Now, let's take the derivative of the top. The product rule, so I will open parentheses. I will take the derivative of the first at the beginning, original second plus original first, and then the derivative of the second. So this whole thing is multiplied. Now why shouldn't I use brackets here instead, so that you can see it better? So this component is the derivative of the top. It should be multiplied with the original bottom function. So I will just leave it like that, x squared ln x. And then we have minus. Then I'm going to place this original function right here, ex sine x. And then I'm going to start brackets. Now I'm about to take the derivative of this component. That is none other than, again, the product rule. So let's use the product rule. First of all, the derivative of the first piece, 2x times ln x plus, and then x squared times original first function times the derivative of the second function. That would be just 1 over x. You can see the simplification of this in the next step. X squared and 1 over x can be simplified in the next step. However, now this is how you can fit it into one single line. But now don't forget, when you get busy with these derivative computations that appears in the denominator, in the numerator of uh, the quotient rule, there is a possibility that you will forget the innocent denominator of the quotient rule. So that quotient rule, let me just move this one all the way behind, I mean after this, so that you can see it better. There is a denominator term in the quotient rule, right? So what is that? Let me transfer this on too, so that we can have everything in one single picture. Now, the denominator is none other than just the square of the denominator. X squared ln x, just square it, and that's our answer. Without simplifications, if you leave the answer, that is our answer. But what matters is to understand this process does not require nothing. I mean, it's not requiring anything more than one single line in computation. Here we have the computation in one single line. The rest is up to the potential simplifications that you can have. All you need to understand when you have different pieces here, when you try to work with different components, what you need to do is to infuse them, like try to understand the structure of the function. First of all, once you look at this, how do you understand it is going to be the quotient rule, not just the product rule right away to begin with? Just look at the overview. Don't even try to read everything. Just look at the function, the structure itself. You can see something over something, a function over a function. That's how you begin with the overview, or the backbone of this problem is none other than the quotient rule, and everything else will be background information. When you need to take the derivative of the top alone, it becomes the product rule, but you need to wait until it appears. But when you try to compute the whole thing, you're going to put the derivative of the first one, the top function, right here, and that's exactly where you're going to employ the product rule. But look at this. The answer, final answer, this is an answer for a quotient rule problem, which is exactly correct because we are dealing with a quotient, a function over another function. So With this, we conclude this lesson. The emphasis is these computations can get very tedious. But when you understand the very basics, it is no, it is nothing complicated compared to the very first example that you worked with here. All you need to understand is the layering of the computations and to see a function and to look at a function and recognize what form and the order of operations that you need to have in the computations. All right, so we will meet in the next lesson.